Hello Class 12. Named reactions are the most common exam questions in NEB Organic Chemistry. In the next 20 minutes, we will master the 15 most asked named reactions, complete with their mechanisms, formulas, and key examples. We'll explore this in 4 sections: alkane preparation, key aromatic reactions, carbonyl chemistry, and finally amines plus Williamson synthesis. Paying close attention is crucial because a solid 15 to 20 marks come from named reactions every single year. Let's get started. Hello, future chemists, and welcome to our first section on named reactions, preparing alkanes and alkenes. We're kicking things off with a classic, the Wurtz reaction. This is a fantastic method for coupling 2 alkyl halides to form a new alkane with a longer carbon chain. The general reaction is straightforward. You take 2 molecules of an alkyl halide, let's call it R-X, and react them with 2 atoms of sodium metal. This must be done in dry ether to prevent sodium from reacting with water. The result is a new carbon-carbon bond, forming R-R, plus 2 units of sodium halide, NaX. For a concrete example, if we take 2 molecules of methyl bromide, or CH3-Br, and react them with sodium, we get ethane, CH3-CH3, plus sodium bromide. The mechanism is a 2-step process. Step 1 involves the alkyl halide reacting with sodium, forming a highly reactive sodium alkyl intermediate. Then, in Step 2, this sodium alkyl attacks another alkyl halide molecule in a reaction similar to an SN2 mechanism, giving you the final alkane. Now for your exam tip. This reaction is best for preparing symmetric alkanes, those with an even number of carbon atoms. If you use 2 different alkyl halides, you'll get a messy statistical mixture of 3 different products, which is usually not what you want. So, remember Wurtz for symmetry. Alright, let's move on to our second method for making alkanes, Kolbe's electrolysis. This one is quite unique because, as the name suggests, it uses electricity. The basic idea is the electrolysis of a sodium or potassium salt of a carboxylic acid in an aqueous solution. This process generates an alkane at the anode. Let's look at the overall equation. 2 moles of a carboxylate salt like sodium acetate, CH3COO, plus 2 moles of water, H2O, undergo electrolysis. This gives us ethane, CH3-CH3, plus 2 molecules of carbon dioxide, 2 units of sodium hydroxide, and hydrogen gas. So what's happening at the electrodes? At the anode, 2 carboxylate anions are oxidized, losing 2 electrons to form 2 carboxyl radicals. These radicals are unstable and undergo rapid decarboxylation, meaning they lose carbon dioxide to form 2 alkyl radicals. Finally, these 2 alkyl radicals couple together, forming our desired alkane, R-R. Here's a crucial exam tip. The alkane formed has twice the number of carbons as the alkyl group of the starting acid. Also, don't forget that hydrogen gas is liberated at the cathode. It's a complete picture. Now let's switch gears from alkanes to alkenes and explore addition reactions. First up is the legendary Markovnikov's rule. This isn't a named reaction itself, but a rule that predicts the outcome of many reactions. It is incredibly important. The rule states that in the addition of HX to an unsymmetrical alkene, the hydrogen atom goes to the carbon that already has more hydrogen atoms attached. The X part, or the halide, goes to the carbon with fewer hydrogens. A simple way to remember it is the rich get richer with hydrogen. Let's take propene, CH3-CH equals CH2, and add HBr. The major product formed is 2-bromopropane, CH3-CHBr-CH3, not the 1-bromo isomer. Why? It's all about the mechanism. In step 1, the proton H+ adds to the double bond first. It adds in a way that forms the more stable carbocation, which in this case is a secondary carbocation. In step 2, the bromide ion quickly attacks this stable carbocation to form the final product. Your key exam tip is that this rule follows carbocation stability. Tertiary is more stable than secondary, which is far more stable than primary. Always form the most stable intermediate. What if we want the opposite result? That brings us to our final topic for this section, Anti-Markovnikov addition, also known as the Kharash peroxide effect. As the name implies, this reaction gives the opposite regioselectivity compared to what Markovnikov's rule predicts. It works for the addition of HBr to an alkene, but only in the presence of a peroxide like ROOR. Let's use our propene example again. CH3 minus CH equals CH2 plus HBr, this time in the presence of peroxide, gives 1-bromopropane, CH3 minus CH2 minus CH2Br, as the major product. The hydrogen went to the carbon with fewer hydrogens. The reason for this reversal is a completely different mechanism. This is a free radical addition, not an ionic one. The reaction starts with an initiation step where the peroxide breaks down to form two RO radicals. An RO radical then reacts with HBr to generate a bromine radical. In the propagation step, this bromine radical adds to the less substituted carbon of the alkene. This forms a more stable secondary carbon radical. This radical then abstracts a hydrogen from another HBr molecule to complete the product. And now for the most important exam tip of all, this peroxide effect only works with HBr. It does not work with HCl or HI due to thermodynamics. Remember that distinction. All right class, welcome to aromatic reactions. First up, the famous Friedel-Crafts alkylation. This is your go-to method for adding alkyl groups to a benzene ring. The general reaction is an aromatic ring, R-H, plus an alkyl halide, R-X. Using a catalyst like anhydrous aluminum chloride, AlCl3, this gives you the alkylated ring, R-R plus HX. Let's see a specific example. Benzene plus methyl chloride, CH3Cl, with our AlCl3 catalyst, produces toluene plus HCl. So, how does this magic happen? It's a three-step mechanism. Step 1, the catalyst, AlCl3, plucks the chloride from CH3Cl to generate a methyl carbocation, which is our electrophile, R+. Step 2, the carbocation, hungry for electrons, attacks the benzene pi cloud. This forms a resonance-stabilized intermediate called an uranium ion. Step 3, to get that precious aromaticity back, a proton, H+, is lost. This gives our final alkylbenzene product. Here's your exam tip: Friedel-Crafts alkylation fails on strongly deactivated rings like nitrobenzene. Also, watch out. The carbocation can rearrange to a more stable form, so you might get a different product than you expect. Keep that in mind. Now for a close cousin, Friedel-Crafts acylation. Instead of an alkyl group, we're adding an acyl group, which is RCO. This is perfect for making aryl ketones. The general reaction is an aromatic ring, R-H, plus an acyl chloride, RCOCl. Using our AlCl3 catalyst, we form an aryl ketone, R-COR, plus HCl. Let's take benzene reacting with acetyl chloride, which is CH3COCl. This gives us acetophenone, a very useful ketone, plus HCl. The mechanism should look familiar. Step 1, the acyl chloride and the AlCl3 generate a resonance-stabilized electrophile called an achillium ion, RCO+. Step 2, this achillium ion attacks the benzene ring, forming the uranium ion intermediate. Step 3, a proton, H+, is lost to restore the ring's aromaticity, yielding our aryl ketone. Time for a very important exam tip. The achillium ion is stabilized by resonance, so it does not rearrange. This makes acylation much more predictable than alkylation. Also, the ketone product deactivates the ring, which neatly prevents any further acylation reactions. One and done. Now for a reaction specific to phenols, the Reimer-Tiemann reaction. This is a clever way to add an aldehyde group, CHO, to a phenol ring, mainly at the ortho position. The general process involves reacting phenol with chloroform, CHCl3, and a strong base like sodium hydroxide, NaOH, under gentle heat. The star product is orthohydroxybenzaldehyde, also known as salicylaldehyde. The overall equation is phenol plus chloroform plus 3NaOH gives salicylaldehyde plus 3 sodium chloride and 2 water molecules. The mechanism is quite unique. Step 1. Hydroxide from the NaOH pulls a proton from chloroform, which then loses a chloride ion to form our electrophile, dichlorocarbene, a neutral carbon with 2 chlorines. Step 2. The electron-rich phenoxide ion attacks the dichlorocarbene, attaching the CCl2 group to the ortho position of the ring. Step 3. Hydrolysis of the attached group under basic conditions magically transforms the CHCl2 into our target, CHO aldehyde group. Now for the exam tip. Remember that salicylaldehyde, the ortho isomer, is always the major product in this reaction. The para-isomer is formed, but only in minor amounts. Our final reaction is the Kolbe-Schmitt reaction, also known as Kolbe's reaction. This is a vital industrial process involving phenols. Here we add a carboxyl group to the ring. We start with sodium phenoxide, which reacts with carbon dioxide, CO2, under specific conditions, 25 degrees Celsius and 4 to 7 atmospheres of pressure. This first step forms sodium salicylate. Then, acidification with a strong acid, like dilute H2SO4, gives the final product, salicylic acid. So how does it work? The phenoxide ion is a very powerful nucleophile. It attacks the weakly electrophilic carbon of CO2, adding the carboxylate group to the ortho position. The intermediate then rearranges to reform the stable aromatic ring, giving us sodium salicylate. The last step is simple protonation. And here's the exam tip you absolutely must remember. This reaction is the industrial route to making salicylic acid. And why is that important? Because salicylic acid is the starting material for making aspirin. Acylation of the product from this reaction gives you one of the most common drugs on the planet. From phenol to pain relief. Hello students. Welcome to section C on carbonyl reactions. First up is the famous Aldol condensation. This reaction involves 2 molecules of an aldehyde or a ketone, which must have at least 1 alpha hydrogen. They react in the presence of a dilute base, like sodium hydroxide. The product is a beta-hydroxyaldehyde or ketone, which we call an aldolol from aldehyde and ol from alcohol. If you heat this aldol product, it easily loses a water molecule through dehydration to form an alpha-beta unsaturated carbonyl compound. For example, 2 molecules of ethanol, that's CH3CHO, react with dilute NaOH to give 3-hydroxybutanol. Upon heating, this loses water to form but 2-enol, also known as crotonaldehyde. How does it work? The mechanism is key. Step 1. The base removes an acidic alpha hydrogen to form a resonance-stabilized enolate anion. Step 2. This enolate anion, a powerful nucleophile, attacks the carbonyl carbon of a second aldehyde molecule. Step 3. Protonation of the resulting alkoxide ion gives the final aldol product. And finally, if heated, step 4 is a beta elimination of water. For your exam, remember this, the reactant must have an alpha hydrogen. Formaldehyde, HCHO, and benzaldehyde have no alpha hydrogens, so they cannot undergo aldol condensation. Next, let's look at the Cannizzaro reaction. This is the counterpart to the aldol condensation. It's for aldehydes that have no alpha hydrogens. What happens here is a self-oxidation reduction reaction, also called disproportionation. In the presence of a concentrated base, like 50% NaOH, 2 molecules of the aldehyde react. One molecule is reduced to an alcohol, and the other is oxidized to a carboxylate salt. For a classic example, 2 molecules of formaldehyde, HCHO, react with concentrated NaOH to give methanol, CH3OH, and sodium formate, HCOONA. Another great example is benzaldehyde. 2 molecules of benzaldehyde in concentrated base will give you benzyl alcohol and sodium benzoate. The mechanism is fascinating. Step 1. A hydroxide ion from the base attacks the carbonyl carbon of 1 aldehyde molecule. This forms a tetrahedral intermediate. Step 2. This is the rate-determining step. A hydride ion is transferred from this intermediate to the carbonyl carbon of a second aldehyde molecule. Step 3. The first molecule becomes a carboxylate ion, and the second becomes an alcohol. So for your exams, the main thing to remember is this: no alpha hydrogen is the absolute requirement for the Cannizzaro reaction. Now for a very useful synthesis reaction, the Rosenmund reduction. This is a brilliant method for preparing aldehydes. The general reaction involves the catalytic hydrogenation of an acid chloride, also known as an acyl chloride. We use hydrogen gas with a special catalyst, palladium deposited on barium sulfate. This catalyst is deliberately poisoned with a substance like sulfur or quinoline. For instance, when acetyl chloride CH3COCl is treated with hydrogen gas over this poisoned palladium catalyst, it is reduced to acetaldehyde CH3CHO and HCl is formed. The mechanism is a surface phenomenon. Hydrogen is adsorbed and activated on the palladium surface. It then adds across the carbonoxygen double bond of the acyl chloride. But why the poison? This is the clever part. The poison, like quinoline, deactivates the catalyst just enough. It reduces the catalyst's activity so that the reduction stops perfectly at the aldehyde stage. Without the poison, the aldehyde would be further reduced all the way to a primary alcohol. So, your exam tip is, Rosenmund reduction is a selective partial reduction, specifically designed to make aldehydes from acid chlorides without overreduction. Our final reaction in this section is the powerful Clemmensen reduction. Its job is simple but important. It completely reduces the carbonyl group of an aldehyde or a ketone to a methylene group, that's a CH2 group. In other words, C double bond O becomes CH2, turning a carbonyl compound into an alkane. The reagents for this transformation are a zinc-mercury amalgam, written as Zn-Hg, and concentrated hydrochloric acid, HCl. For example, if we take propanol, which is acetone CH3COCH3, and treat it with the Clemmensen reagents, we get propane CH3CH2CH3 plus water. Another example, benzaldehyde can be reduced to toluene. The mechanism is quite complex and involves intermediates called zinc carbenoids on the surface of the amalgam. Fortunately, you don't need to know the detailed mechanism for your NEB exam. What you must know is the transformation and the conditions. Here's a crucial exam tip: the Clemmensen reduction is performed in a strong acidic medium. This means it's unsuitable for compounds that are sensitive to acid. For those, we use the Wolff-Kishner reduction, which achieves the same CO to CH2 conversion, but in a basic medium. Both are very important. All right, class, let's dive into our first reaction, the Hoffmann's bromamide degradation. It's a fantastic way to shorten a carbon chain, also known as the Hoffmann rearrangement. This reaction converts a primary amide into a primary amine with one less carbon atom. The general reaction is a primary amide reacting with bromine and 4 equivalents of potassium hydroxide. This gives you a primary amine, potassium carbonate, 2 potassium bromide, and 2 water molecules. For a specific example, let's take acetamide. When you react acetamide, that's CH3CONH2, with bromine and potassium hydroxide, you get methylamine, CH3NH2. See that? We went from a 2-carbon amide to a 1-carbon amine. Now for the mechanism. Step 1, the amide reacts with bromine and base to form an N-bromamide. Step 2, another base molecule pulls off the proton from the nitrogen, creating an anion. Step 3 is the key rearrangement step. The R group migrates from the carbonyl carbon to the nitrogen, kicking out the bromide ion to form an isocyanate, RnCO. Finally, step 4, the isocyanate is hydrolyzed by water, which gives our final primary amine and carbon dioxide, which is then trapped by the base. And here's your crucial exam tip: remember, 1 carbon is always lost in this reaction. This method is specific to primary amides and is a key step-down reaction in organic synthesis. Next up, we have the incredibly useful Sandmeyer reaction. This reaction is a cornerstone for introducing various substituents onto an aromatic ring, starting from an amine. First, we need to prepare our starting material using a process called diazotization. We take aniline, react it with sodium nitrite and HCl at a very cold 0 to 5 degrees Celsius. This produces benzonediazonium chloride. Now for the Sandmeyer reaction itself. You take this diazonium salt, C6H5N2 plus Cl-, and treat it with a cuprous halide like copper 1 chloride. The result is chlorobenzene plus a harmless puff of nitrogen gas. This is a fantastic way to replace an amino group with a halogen. You can make variations too. For a bromosubstituent, use copper 1 bromide with HBr. For a cyano group, or nitrile, use copper 1 cyanide. The mechanism is believed to be a radical pathway catalyzed by the copper 1 ion. The aryl radical formed then attacks the halide source. And now for a very important exam tip, this reaction has specific needs. To make fluorobenzene, you need a different named reaction, the Baltz-Schiemann reaction. And for iodobenzene, it's even simpler. You just need to add potassium iodide, no copper catalyst required. Our final reaction for this section is Williamson's ether synthesis, the classic method for making both symmetrical and unsymmetrical ethers. The general reaction is simple. A sodium alkoxide reacts with an alkyl halide. This gives you your desired ether plus a sodium halide salt. It proceeds through a clean SN2 mechanism. For a concrete example, if we react sodium methoxide, that's CH3ONA, with bromothane, CH3CH2Br, the product is methoxyethane, a mixed ether, plus sodium bromide. It's a straightforward nucleophilic substitution. Let's break down the mechanism. The alkoxide ion is a strong nucleophile. It performs a backside attack on the partially positive alpha carbon of the alkyl halide. As the new carbon-oxygen bond forms, the halide ion leaves, and we get an inversion of configuration at that carbon, just like any SN2 reaction. Now, pay close attention to this exam tip. For the best yield, you must use a primary alkyl halide. If you use a bulky, secondary, or tertiary alkyl halide, the alkoxide will act as a base, and elimination will become the major side reaction. This means you cannot make an ether with a tertiary alkyl group attached to the oxygen via this specific route. Always pick the less hindered path. All right, class, let's recap our 15 named reactions. Group them mentally. First, alkane preparation. Wurtz reaction joins two alkyl halides with sodium to make a symmetric alkane, and Kolbe's electrolysis makes alkanes from carboxylate salts. Next, addition reactions. Remember Markovnikov's rule, where H adds to the carbon with more hydrogens, and Anti-Markovnikov using peroxide, which is the reverse. Then, aromatic reactions. Friedel-Crafts alkylation and acylation add groups to benzene. Reimer-Tiemann gives salicylaldehyde, and Kolbe-Schmitt gives salicylic acid. For carbonyls, Aldol condensation requires an alpha hydrogen, Cannizzaro does not. Rosenmund makes aldehydes, and Clemmensen reduces C-double bond O to CH2. Finally, miscellaneous Hoffmann bromamide degrades amides, Sandmeyer uses diazonium salts, and Williamson makes our ethers. Now for exam strategy. NEB asks about these reactions in three main ways. First, convert X to Y questions where you must choose the correct named reaction. Second, complete the reaction where you provide the products. And third, name the following reaction where you identify the process. To score full marks, here are my top tips. Always draw the full structural formula. Always mention the specific reagent and catalyst conditions, like anhydrous AlCl3 for Friedel-Crafts or ZnHg/HCl for Clemmensen. Add temperature if it's crucial, like for Kolbe-Schmitt. If a mechanism is asked, write it in numbered steps. Remember, these reactions are crucial, often worth 15 to 20 marks. Hello students! Let's master named reactions with some simple mnemonics. First, remember Wurtz with sodium, symmetrical results. It uses sodium metal to couple two identical alkyl halides, giving you a symmetrical alkane. Next, Rosenmund rescues aldehydes. This reduction of an acyl chloride stops perfectly at the aldehyde stage. Then, contrast two similar reactions. Clemmensen cleans with acid, Wolff-Kishner works with base. Both turn a carbonyl into a CH2 group. For amides, think Hoffmann halves a carbon. The Hoffmann bromamide degradation removes one carbon atom. For diazonium salts, Sandmeyer swaps with salts of copper. And finally, Williamson weaves ethers and alkoxide plus an alkyl halide gives you an ether. These phrases make recall instant. Now, let's look for patterns. It's like learning one idea instead of 5. First is the carbonyl reduction family. Clemmensen, Wolfgischner, Rosenmund, and even LILH4 all target the C-double bond O group, just with different outcomes. Second, see the electrophilic aromatic substitution pattern. Friedel-Crafts, nitration, and halogenation all share the same rhenium ion intermediate mechanism. Third, think of diazonium salt reactions as a group. The N2 group is an amazing leaving group, and you just swap it for something else. Finally, base-promoted carbonyl reactions like Aldol or Cannizzaro depend on one thing, the presence or absence of an alpha hydrogen. Recognizing these families simplifies everything. Excellent work! You've just conquered 15 essential named reactions. Remember the highlights: Wurtz, Kolbe-Markovnikov, Friedel-Crafts, Reimer-Tiemann, Aldol, Cannizzaro, Rosenmund, Clemmensen, Hoffmann, Sandmeyer, and Williamson. If this helped, subscribe and like the video. Drop a comment on what to cover next. Coming up is a deep dive into the Lucas test. Remember, these reactions are guaranteed marks.